So now we're going to finish up lecture by talking about gas exchange as well as oxygen dissociation curves and what can ultimately affect those in terms of conditions in the blood. So with our oxygen, transporting that in the blood, we learned from the previous unit that is transported by hemoglobin, one of your blood proteins, that occupies a lot of your red blood cell volume. Your hemoglobin is able to bind ultimately 4 oxygen molecules. And the bulk of your oxygen is transported this way. A little bit of the oxygen is dissolved in the plasma, but it is largely transported by hemoglobin. Then for carbon dioxide, it can be transported in a couple different methods. Most of your carbon dioxide is going to be transported in what's called bicarbonate ions. Second, most of it is going to be in combination with various blood proteins. And lastly, the least amount is going to be in the plasma, like your oxygen. So carbon dioxide, when it enters this bloodstream, is able to combine with water in a red blood cell to basically form what's called carbonic acid. That is the structure right here. And ultimately, your carbonic acid can dissociate to form a bicarbonate ion and hydrogen ions. So your CO2 right here mixes with water and forms your carbonic acid. This occurs with the enzyme carbonic anhydrase. If you don't have carbonic anhydrase, you don't have any production of carbonic acid. Then that carbonic acid dissociates, which just means it breaks down, into hydrogen atoms, which are responsible for the pH levels, and your bicarbonate ion. So I will say for with the carbon dioxide structures, make sure you know both the chemical formula and the words for the molecule. So for example, with your bicarbonate ion right here, bicarbonate, make sure you know bicarbonate and you know that bicarbonate means H3O or HCO3 minus. Largely because a lot of times you'll see the molecule formula in the text or in diagrams, and oftentimes they'll also be in words. So just be familiar with both forms as you can kind of flip-flop back and forth between them. Same with your carbonic acid. Okay, so with CO2, like I mentioned, when it diffuses from tissues back into the blood, only a small amount of it is dissolved in the plasma. Most of it goes into the red blood cells. And of that, most of that is converted to your bicarbonate ion, your H3O or HCO3 minus. Then the rest of it is bound to hemoglobin. So in terms of all the things that are going on while this gas exchange happens with your CO2 and your oxygen, your book has 2 different figures that show you everything that's going on. As a caveat, the book sort of makes it seem like there are 7 steps that are occurring all subsequently. So like 1, 2, 3, 4, 5, 6, 7, with the previous steps being reliant on the step prior to that. Wait, it doesn't make sense. Sorry, with the step being based on the previous step. That's not necessarily the case. A lot of these things going on in the red blood cells are happening concurrently at the same time. So just a heads up, I have all 7 steps here as written in your book, but just know that some of these things are happening at the same time and some of them are based on a previous step. I'll go through each step, quote unquote, in turn. But for these diagrams, I'm just gonna be following the general pathway of the arrows and point out all of the different steps along the way. So first thing, your carbon dioxide is step 1, is gonna diffuse from the high partial pressure in the tissues to the lower partial pressure in the red blood cells. Pretty straightforward. That carbon dioxide can do 2 things. It can either mix with water and along with carbonic anhydrase become carbonic acid, or it can ultimately do step 7 and bind with your hemoglobin. I'll cycle back to that in a second. That carbonic acid can dissociate or break down into your bicarbonate and your hydrogen ions. Those hydrogen ions can then bind to your hemoglobin. That's what HB is. And when those hydrogen ions bind to that hemoglobin in step 6, that oxygen will be released. This is what's known as the Bohr effect. Basically just means as we lower pH, meaning we have more hydrogen ions in the blood, more of those will bind to hemoglobin and force oxygen to be let go of. Additionally, when we have the release of oxygen, that carbon dioxide I mentioned a moment ago can also bind to hemoglobin. This is what's known as the Haldane effect. It just means that when oxygen gets released, that it frees up space for carbon dioxide to bind to hemoglobin. Okay, so then now we're on to step 4. Like I said, this doesn't go in a particular order. That's why I didn't really like the way the book presented it. At station 4, we have what's called a chloride shift. What that means is some of your bicarbonate ion is going to leave the blood and go into the plasma. However, to counteract this, some chlorine ions, which are also negatively charged, like your bicarbonate, are going to diffuse into the blood cell. So sort of to maintain an ionic equilibrium, when bicarbonate leaves, chlorine comes in. So those are all the steps associated with gas exchange and are in the tissues. And we do the exact same thing, but just in the reverse for gas exchange in the lungs. Again, this is not necessarily saying that all these steps occur in the exact order. Some things can occur at the same time. But following the arrows and going through all of the stations, your oxygen right here has high partial pressure in the alveoli and has low partial pressure in the lungs. It's going to diffuse from the oxygen or diffuse from the alveoli to the lungs along that partial pressure gradient at step 5. And then that oxygen can bind to hemoglobin if enough hydrogen ions have been released at step 6. Again, this is the Bohr effect, so we would be decreasing pH in this case because the hydrogen ions would then go on to combine with bicarbonate, freeing up space in the hemoglobin, allowing for oxygen to bind. When oxygen binds, that prevents carbon dioxide from binding at station 7. So again, this is the Haldane effect. If we have oxygen bound to hemoglobin, carbon dioxide is not going to bind or is less likely to do so. If we don't have oxygen bind, carbon dioxide is more likely going to bind to hemoglobin. So again, back at station 6, those hydrogen ions can combine with your bicarbonate ion and form at station 3 your carbonic acid. Your carbonic acid can then, with the help of carbonic anhydrase, that's the enzyme there, can form water and CO2. And then some of that CO2, whether it came from being released by the hemoglobin or being formed by the carbonic acid and the enzyme to CO2, will then diffuse from high concentration in the red blood cells to diffuse from high pressure. I misspoke. Diffuse from high pressure in the red blood cells to high pressure in the alveoli. And then lastly, again, we have at station 4, the chloride shift. When chlorine leaves the cell and enters the plasma, your bicarbonate ion can diffuse in to the red blood cell, again, to keep that equilibrium. So a couple different things can ultimately affect the partial pressure of oxygen transport. And the way we notice this effect is what's called oxygen saturation. What that is just saying is what percent of hemoglobin have oxygen bound to them in comparison to all of the hemoglobin. So for example, if I had, just to keep it real simple, 100 hemoglobin proteins in a sample of blood, if 73 of them had oxygen bound to them, that is a 73% oxygen saturation. So 73% of all, or 73% of the hemoglobin have oxygen bound versus the 100 hemoglobin molecules. And we measure this by what's called an oxygen hemoglobin dissociation curve. This is just showing the relationship between the percent oxygen saturation as we change different partial pressure values of oxygen. And it looks a little something like this. So on this figure right here, we have a graph of the percent oxygen saturation. Again, that's just the percent of hemoglobin with oxygen bound compared to the total number of hemoglobin, graphed against your partial pressure of oxygen on the x-axis. So as we see this general positive trend, so as we increase partial pressure going from the tissues to the lungs, we see an increase in oxygen saturation. That makes sense because at the lungs, that's where they're receiving the oxygen molecules, so it makes sense that more oxygen is going to bind at the lung site where we're directly getting oxygen from, versus at the tissues where we're dropping all the oxygen off. So if we start at the right end, we see the partial pressure in the lungs is about 104 roughly. We're at pretty much 98% of saturation. So they give a little example with the beaker over here. If the oxygen, if you will, is sort of like a liquid, so the glass is the total amount of saturation we have 98%. So at the 104 partial pressure in the lungs, 98% saturation. 98% of those hemoglobin molecules are oxygen bound, or have oxygen bound, excuse me. Then as we decrease the partial pressure and get to the partial pressure of oxygen in the tissues at rest, so while not doing any sort of a physical strain, partial pressure is now at like roughly 40. So from 100, or sorry, from 98% to roughly 75%, we have 23% of the oxygen get released that was bound, because we have to get, again, oxygen from our lungs to our tissues. So some of that oxygen is going to get released to the tissues. Then as we go even further down to roughly, let's say 15 about partial pressure, this is the partial pressure of the tissues during exercise, so much lower than at rest. So now we see, again, we're going from about 75% saturation to about 25% saturation. So we have a release of 70% of the oxygen bound. Again, this makes sense because we want to have more oxygen getting to the tissues, because the tissues really need that oxygen during exercise. So with this oxygen dissociation curve, we have what's called the Bohr effect. I mentioned this a second ago when we were looking at the gas exchange diagram with oxygen and CO2. But again, this is just the idea that as you have pH go down, become more acidic, you have more oxygen get released from the hemoglobin, because your partial pressure of the oxygen is also decreasing. And this is because you have more hydrogen ions within the blood, and those hydrogen ions will bind to your hemoglobin, ultimately altering its shape. And as we know from like introductory biology courses, structure affects function with a lot of biological systems. So by changing its shape of the hemoglobin, you change the function and make it not as efficient at binding oxygen as it used to be without the hydrogen ions bound. So take home message, as you decrease pH, you decrease the amount of oxygen bound to hemoglobin. Then additional things that can ultimately affect the amount of oxygen being bound are CO2 and temperature. So as we increase the partial pressure of CO2, have more CO2 in the system, we have a decrease in pH. And this is because you have your carbonic acid formed by your carbonic anhydrase, catalyzing the reaction between CO2 and water. And then that carbonic acid is going to break down to your hydrogen ions, which are, again, responsible for your pH levels, and that bicarbonate ion. Then with temperature, it's going to have a tendency to, when we increase temperature, lower the ability of oxygen to remain bound to hemoglobin. Similar idea to with your acidity level. So when you increase temperature, you're changing the shape a little bit of the hemoglobin protein, and ultimately that makes it less efficient at binding oxygen. Then we have a compound that can also affect hemoglobin binding called BPG. This just stands for 2,3-bis-phosphoglycerate. I will always just refer to it as BPG from here on out for simplicity. And this is just a compound that gets released as you break down glucose when you're metabolizing energy. When you have more of this compound in the red blood cells, those will also bind to hemoglobin and ultimately cause the release of oxygen. So if you have more BPG in your blood, you're going to have less oxygen bound. So with our oxygen dissociation curves, we have the shift going on, showing the effects of decreased pH, increased CO2 levels, and increased temperature. So I'm drawing my mouse, or I'm moving my mouse over on the red line. That is the curve before the shift, what I showed you in the previous figures. Then when we either have decreased pH levels, increased CO2 levels, or increased temperature, that curve is going to shift to the right. So it's going to move over. And it is now represented by this blue line that I'm moving my mouse over. So in terms of what this actually means, is that when we have this shift, we're going to have a result in that there's going to be an increase in the release of oxygen. So where we have the partial pressure of oxygen in the tissue here, again, this is roughly like 15 when we're doing exercise. Normally would have about 32% roughly of saturation if we were under just normal conditions. But when we have these decreased pH, increased CO2, or increased temperature, we have a lot less saturation because all this oxygen is being released to the tissues under these conditions. Then on the other hand, if we have a large increase in pH, large decrease in CO2 levels, and large decrease in temperature, our blue curve right here, the curve before the shift, is then going to shift to the left. So it turns into this red curve we see right here that I'm bringing my mouse over. So in this case, what's going to really be noticeable is that in the lungs, so roughly at 104 is our partial pressure of oxygen in our lungs. It's going to lead to an increased ability of hemoglobin to pick up oxygen. So normally before the shift, it was roughly like 90, 95%. And now at this shift, it's pretty much at 100% saturation. So having these changes in conditions with pH, with CO2, with temperature, even with BPG, ultimately can impact if the hemoglobin is going to drop off more oxygen at the tissues or even be able to pick up more oxygen at the lungs. So that is all we have for this chapter. I will see you all next week when we start the digestive system.